ROS2 Nav2 stack is a very powerful tool for developing autonomous robots quickly. In terms of ease of use as compared to ROS1 navigation, it's on a completely different level. It is now simplified to the level of using as a library. So in this lecture, we are going to be integrating ROS2 navigation stack Nav2 into our Turtlebot 3, giving multiple goals and making the robot go through all of those waypoints. If I simplify it for you, autonomous behavior of robot given the goals only required three things: the world, the environment, then the map through some 2D mapping technique, and then the navigation stack. We integrate all of these three things and we will obtain autonomous behavior of Turtlebot 3. So let's utilize Turtlebot 3 from PCL lecture and start integrating navigation stack. This lecture is focused with this specific issue that is created in ROS2 learners repository, link in the description, and we are going to be filling this issue and committing it to be done. We'll use Turtlebot 3 for mapping, navigation pipeline setup in Turtlebot 3. It's going to be simplified for you, and write a node to send goal commands. Let's start with our VS Code. Here we have this ROS2 learners package, and here we have our navigation package that we created for occupancy grid. Now I am going to bring up the terminal and I'm going to first install Turtlebot 3 package for my specific version of ROS that I'm using, that is ROS Humble, Turtlebot 3 and simulation. This is the package that is required. You have the option of downloading it or otherwise cloning it into your repository, but you have to make sure that you go into the Humble Devel and you use GitHub -b Humble Devel and this git link. So you clone the exact version that we require. With this package, we also need Turtlebot 3 messages package, which is already installed. Okay, now once we have that, we need to run the simulation. If we go here in Humble Devel Gazebo, we want to bring in the simulation. I understand that inside of the launch file there is a Turtlebot 3 world launch file that I want to run. So I am just going to ROS2 launch Turtlebot 3 Gazebo and Turtlebot 3 world launch. I'm pressing tab, it automatically completes. I'm going to press enter. It is going to give me an error, and that error would be regarding Turtlebot 3 version that we are using. It will spawn the world but not the Turtlebot, because it is designed in a way we have to tell which model of Turtlebot. So this export command of a variable available to the system environment is required. I say that export Turtlebot 3 model as waffle. There are three different models. We are only interested in waffle right now. So here we have our Turtlebot, and this is the world. You can see we have the LiDAR. We have already done it in point cloud series. Coming to the next thing, which is driving the robot, and before that we need to understand what are the available topics so we can publish on a specific topic that tells us about how to drive the robot. And because in ROS the general term used for driving the robot is command velocity, and we know that we can publish on the topic for driving the robot with the help of teleop. ROS2 run teleop twist keyboard teleop twist keyboard. This is the node that helps us to drive anything that utilizes command velocity, as in the scenario of our Turtlebot. So it is moving. We can drive it. These blue lines are the lasers that are moving as well, and these dark blue tells us it is gliding with an obstacle. Light blue tells us about not touching anything to a certain of defined area that we have. Now we have to look into some important things. If I just perform ROS2 topic list and make it bigger, you can see we have camera related things. We are not interested in that. Then we have command velocity and odom, which is very important, and scans. These blue lines I was talking about are the laser scans that we are getting from this specific topic. Laser scans are going to be required for building the map. This scan topic and odom topic. For making a map, let's first understand why we need a map and how we can build it. The example we are working on is an indoor mobile robot, and the robot does not know anything about the environment it is working on. So we use LiDAR, a sensor that sends light and gets it back and measures the distance. So something that is away from the robot is calculated with quite a lot of accuracy. So in this scenario, occupancy grid is produced, we have discussed in the previous lecture of the playlist. So the main task that is happening with LiDAR is the mapping process. Mapping process utilizes two main things: the laser scanner, that is known as the LiDAR, and the odometry of the robot. So it knows where the robot is moving and the scans it is producing from the sensor. Algorithms commonly used with ROS are cartographer and G mapping. We will be using cartographer. There is a lot of detail about that on the internet, so I will not be going into that, just integrating into our robots. We will be producing map. It contains 3 states, each map, which is known as an occupancy grid: free state, occupied state, and unknown state, meaning we don't know about that area. As probabilities are also involved, so things are going to get whiter and whiter in color. So those are points which are getting more and more values of being a free state until they are 100% white. Black is occupied state. So we create a map of the environment given the proper odometry, so that we understand in the environment where are the obstacles and which spaces are free, and the robot can travel in those free spaces only. So we need to first create the map using cartographer. Let's do it. For mapping purposes, we will utilize launch files because that makes our life quite easy, and config directory as well, which will contain all of the configuration files for mapping, navigation, and all that stuff. So once we have created these two, we have to add it into CMake list. Otherwise, the content of these two directories are not going to be available to us. In CMake list, I will say install a directory. The name of directory is launch. The destination is going to be share of our project name or package name, and inside of that create a launch file and copy all of the content of launch file into this specific path. Also do the same for config directory. In launch directory, I will create mapping.launch.py. For basic structure of our launch file, we have a generate launch description in which we define all of the nodes we have. So there are going to be 2 nodes. Both nodes are going to contain a package, an executable, name, and output option. For the package, we are going to be using cartographer ROS. Make sure you have already installed it. Sudo apt get install ROS humble cartographer and -ROS. I already have that, so I don't need to install it again. Cartographer ROS is the name of the package. The executable inside of it is ROS to run cartographer. ROS double tap, it tells me about the available nodes. I am interested in cartographer node that runs the main code for cartographer. So this is the node and I want to name it to be mapping node. This is what we can assign by our own self. Output of this should be displayed on the screen so I can see what is happening, what are the logs it is telling. There is also an argument tag that we will fill. First, let's complete the second node. I'll copy it and I'll paste it for the second node. For the second node, the package is same, the cartographer, but the node is occupancy grid that deals with the publishing of occupancy grid from submaps. Name is going to be occupancy node, so we can distinguish between these two. I want to also log the things from it. We don't have the arguments from this specific one. Regarding the arguments, we have a lot of options, but how do we know that? We are going to go to the repository, which is of cartographer ROS, and specifically to get this executable, we have to look into this project, which is cartographer project by ROS. And here inside of the scripts, we have this node main and occupancy grid. You can check from the CMake list as well. So if I open node main, there are already defined arguments that we can provide. So we would be filling out this configuration directory, and the scripts tell us what arguments does this node require. So configuration directory and base name is what we are going to be using. Second one is going to be configuration base name, and we will provide the names. What they are actually doing is, it says the directory in which configuration files are searched, and the base name of the file that we will use as a configuration for this cartographer. I am going to be taking the file from turtlebot3, which is already set. If I go into the humble branch here, and in humble branch we have cartographer, and in config folder there is a file that defines everything that a cartographer requires for the mapping purpose. Let me bring this into my VS Code, and here in config folder we have this file. We have to now provide path to that file. So cartographer node can utilize this specific file. We'll start with providing path to the specific directory, which is config directory. I will write it. For Python to access this, I will use the os.path.join get package share directory where all of the files are placed through CMake list. Name of our package is navigation underscore and the directory it contains is config. This is what is the location of config in the shared directory. Our configuration directory is there and inside of that there is this file which I will directly provide. So if we take a look here, cartographer node taking this specific file which is configuration file for our mapping purpose, and it is going to then launch occupancy grid, and both of these are going to log on the screen. If I go into my terminal, perform colcan build, it has already finished. So in this specific terminal which was utilized to launch the turtlebot, this export line is already there. I will put it into my bash rc script so all the terminals can access it, otherwise I have to copy paste again and again. .bash rc file, I will just put it here. As our variable is set, now run the node for bringing the robot and the simulation. ROS2 launch turtlebot3 gazebo turtlebot world launch py. Let's launch it. In the next terminal we need to run our cartographer node. We have this. Let's perform colcan build and then ROS2 launch navigation underscore mapping.launch.py. So we have to check if it has successfully loaded the configuration file, and in our scenario it has done that, is as it says found something. Although there are some warnings regarding the frames, that does not affect us right now. We have to first check if the map is being built or not. So I will open up RViz2. In RViz2, fixed frame should be on map and robot model should be involved, but most importantly a map and odometry should be added. In map you are going to add the topic to map. It is going to appear on the screen. Coming to the odometry, it should take odometry from here. I'm going to save this file as we don't need to add again and again. I want to add it into our navigation config file and I'm going to call it mapping.rviz, as from now on we will automatically load this file from the simulation, and from the RViz we are going to build the map while we are driving the robot. I think this is the orientation. From terminal I'll open up another one. This one is going to run the teleop node which drives the robot. As I move the robot forward, you can see the map is being updated. Let me clear the screen, and it is moving and it is continuously updating the map on RViz. So what you need to do, you have to move your robot to all places which are not white enough, so free spaces becomes visible. Once this map is created on RViz, you are going to save this map. This is the most important step. I am going to go inside my repository, which is in source directory of ROS2 workspace and learners, ROS2 learners, and there I am going to go inside the package, list it. It contains config, include, launch and stuff. I'm going to save the map in config by this command, ROS2 run nav2 map server. That's a map server and there are multiple nodes of it. We are going to utilize map saver CLI, which means save the map through command line. That this is what it does. -f name of the file, tb3 map is what is going to be the name of the map. If I open up VS Code in config file, we don't have that yet, but when I press enter, you can see a map.pgm is created and map.yaml is created. If I open up the folder, you can see this map image is being produced, which is currently the map produced in our RViz. We have the map and now let's plug in the nav2 stack. But before just plugging it, we need to look at nav2 from 4 aspects: AMCL node, Adaptive Monte Carlo localization is just going to be about localization, that is going to give predictions, estimates about location of the robot inside of the map, where it is going to be, where it was, something like that. The second thing is BT Navigator, which is Behavior Tree Navigator, which simplifies a lot of complex robot behavior for us to just give goals and it navigates using behavior trees. The third part is cost maps. So there are two cost maps, global, local cost maps. Global is going to be looking through the map and local is going to be getting the sensor data. Fourth point is planners. Planners are the most important part of navigation stack because they provide you about the motion plan that you are producing, utilizing the cost maps as well. You can also write your own planners, but in this lecture we are going to be using DWB planner. And the most interesting thing about this whole navigation stack integration is, in programming we are just going to add one launch file into our pipeline and it is going to plug in nav2 stack. All of the navigation to stack 4 aspects that we discussed are going to be controlled through one single configuration file that is of extension YAML or YAML. All of the parameters of those 4 aspects are going to be written there. We can change them and we will see how changing them will affect the simulation. So let's first take a look what installations you need to move forward. Before getting into the navigation integration into our Turtlebot 3, you have to install these packages. This markdown is provided into this navigation directory, installations.md. You can directly install them and get the navigation stack working. We will start from the point of creating a new launch file. I will create a copy of the mapping one. I will call it navigation.launch.py. This is going to bring robot, map, navigation stack and ROS, 4 things. Let's start with including our map file. As this config directory is with us, we just need to provide the name. We are going to say map file is equal to os.path.join config directory and name of our map file, which is tb3 map.yaml. Now this whole path is stored in this map file in this variable. Now let's remove this node because now we are not mapping, we need ROS here to give control over the map navigation. It's going to be ROS to node and output should be on the screen. To run the robot we need to include a launch file. To run the launch file of our robot we need these 2 functions and we will utilize them in launch description. Include launch description. We will launch a Python launch description source. It is going to be from a package, then a launch directory and the name of our launch file. I'll fill these values with the help of this specific command. The package name is Turtlebot3 gazebo. So we will say get package share directory of this specific package. And launch should be directory in which the launch files are placed. In our scenario we have mapping and launch navigation. Name of the launch file is this Turtlebot world launch. Similarly, if you want to run a mapping launch file, we would say get package share directory of navigation and launch file and mapping.launch.py. This will bring ROS2 and Turtlebot 3. You should also provide the directory explanators and perform calcon build so it can load this navigation launch file ROS2 launch navigation launch.file. It should bring the waffle robot and ROS as well. So our launch file is bringing a robot and ROS. Now we just need to provide ROS specific configuration and the navigation stack integration. For navigation stack things are quite easier. We are going to copy and paste this launch description, and for navigation stack we are going to use this launch file ROS2 launch nav to bring up, and there is a bring up launch file. That is what we are going to be using. So this is the package name, launch directory, and this is the launch file name. It is simply arranged in this manner that we have already set all of the things and just run this launch file with some arguments. Launch arguments are map, that is what navigation stack requires, and the parameter file. This parameter file contains all of the configuration for the navigation stack. To fill the values we'll just put the map file here and parameter file here. Parameter file is going to be given similarly as map file is going to be given. tb3 nav params. It is going to be a YAML file, but it is going to contain a lot of explanation. So let's go through that first. So open up your config directory, new file, tb3 nav2 params .yaml. I'm going to save that, nav2 params, and we are going to go through these parameters step by step, although they are a lot and most of you might not be needing all of these right now. When we will launch this launch file, it is going to bring the robot and the navigation stack integrated and the ROS2 with the configuration I will mention, and this navigation stack is requiring a map file that we saved and the navigation parameters. So navigation parameters come in 4 different parts: AMCL and BT navigator, then controller server, local cost map, global cost map, and map and waypoints follower. So these are the main things that this whole parameter file contains. You can divide them as well. Most important one is global and local planner that you will see in just a minute. You can directly make changes in these parameters. I will change some of these and you will see the result of that. So I think before going into the detail of this, let's first run it and then we will make some changes and see what these changes are going to affect. So the source of this parameter file is from official Turtlebot 3 navigation 2. There are other parameters file for all of the models as well. I have also added the ROS configuration file obtained from Turtlebot 3 website because it saves a lot of time to add all of these things in ROS, and that has been provided as an argument to ROS2 node running. So let's perform Colcan build and now launch our navigation launch file. So let's put it side by side. This ROS configuration file contains a lot of things. So this is our top view, and if I set my map here at this specific point, currently you might see that there is a global status error for the transform. As soon as I press this 2D pose estimation and I give the pose of the robot manually, that robot is looking at this specific side, this warning goes away and a lot of colorful things are appeared. These things are actually from the parameters we have. Now we have told the ROS simulation that our robot is at this specific point, and now you can understand where this whole map is. This whole map is already obtained from the map we saved. Now let's do the autonomous navigation part. I'm going to click this nav2 goal here and I'm going to give it to a certain free area, that is this white space. I'm going to put my arrow and give an orientation as well. Let's make it look at this specific point. A path has been generated. In simulation, the robot is also moving. Our first goal has been reached by a robot. Let me give another goal at this specific point, and you can see robot is moving, as well as there is a blue line as well that robot is following. That is a local planner. This is the DWB planner with a window, and there is a path with probabilities as well. Let's quickly look at the parameter file, and in parameter file this AMCL node is happening near the robot, and near the robot you can see these small arrows. These are probabilities of a robot future pose, and this AMCL parameter, which is adaptive Monte Carlo localization used for robots. If I give a goal, you can see these arrows are actually predicting what should be the robot's next location. So they are moving, they are iterating, and they are somewhere before the robot as well. So this AMCL is dealing with robots localization part. BT navigator is actually behavior tree parameter that we can play with. It requires the global frame or DOM topic. If the names of the topic from your robot are not the same mentioned here, it is not going to work. We have multiple things that we can play with, but I will not make any changes. The most important thing to me are local and global planners. So here, if you can see, this local cost map contains a width of 3 and 3 height. If I show you this, it is talking about this window. If I close this simulation as well as I close the gazebo, and I make the change into 1 by 1 window for the local planning. I stop it and rerun it again, make changes, save, perform calc and build first and run it again. First I need to tell the location of the robot. This is my robot, and if I give a goal here, now if you can see here, the window, the local window around the robot is now very small. It is equal to 1 by 1 square. That is equal to the grid that is beneath it. Previously it was 3 by 3. So you can see the local planner is now only going to consider things inside of this window. So the planning is now less computationally expensive, and it is going to be not very much robust as well, because it is considering things only in this window. So that's how you can change the parameters, and they are going to directly affect the autonomous behavior. So I'll put them back, although it is working fine, but in real world it might cause some problems. Coming to the point of plugins, the blue lines in the simulation are because of this inflation layer. And in inflation layer, if I introduce the inflation radius to 0.3 from 1, and also from the global cost map inflation radius, if I reduce it to 0.1, both of the inflation radius are reduced. Let's see what is the effect. First perform calc and build and launch the file. Then I give the estimated pose, and you can see the inflation radius has changed drastically. Although this inflation radius around the obstacle can also be reduced by making the changes in the parameter, and now the free space is more visible to the robot, and you can see it is also planning from the radius of voxel layer inside of the map. So you can play with these parameters a lot and see what suits best for you and how much radial obstacle avoidance your robot should perform. Here I want to show you one very interesting feature of navigation stack. If I click here waypoint nav through pose mode, it provides us the option to give multiple goals to your robot's navigation. I give the robot this specific point, then select nav to goal this specific point with a specific orientation, but I don't think so it is going to follow the orientation. I give this point and I say reach this point. So there are 4 goals that I have provided to the robot. It's sort of multi-goal or waypoint navigation, and I say start nav through poses. Navigation stack has now activated, and it is going to go to each of these nodes 1 by 1. So as you can see, the robot has passed through all of the goals. You can plan it to perform very amazing projects. I really enjoyed when I first saw this multi-waypoints robot following in the map. Although sometimes it works, sometimes we have to make the changes into the global cost maps and local cost map, but it still works. Recovery behaviors otherwise starts to work. The thing is, with nav to stack, integration of autonomy into a robot is becoming really easier in the simulation and in the real world as well. I will give example of that as well. So if I recap here what we have done, the first thing we did was to bring the simulation and make the robot move manually. The second thing was mapping. Cartographer ROS node was utilized to produce a 2D map, and we drove the robot around the environment to build the proper map, which is basically an occupancy grid. Then we integrated nav to stack, and the integration was done on 4 different aspects: localization, navigator BT, planners and cost maps. We made the changes in the parameter in the YAML file, and it was directly impacting robots planning in the environment. Then we utilized ROS to send different goals, single goal, multi goals, and the robot was properly following all the waypoints. It was interesting, it took some time, but in the next lecture we are going to be giving goals to our robot using Commander API in Python to this specific robot, and that is going to be done through nodes, Python nodes, which is going to be really interesting because that's how you truly make your robot autonomous, not by giving manual goals through ROS.